Very shortly, we're going to get into a discussion of streams and parallel streams and how you program them more deliberately, and we'll show some examples that show tremendous speed up if you use parallel streams. But I would be remiss if I didn't give you a little bit of some caveats ahead of time, warning you about the fact that everything is not rainbows and unicorns. There are potential downsides or hazards with parallel streams. And the more you're aware of that up front, the better you'll be programming parallel streams. So we'll talk about some of the ways to avoid these problems. Some of these problems are similar to the problems we talked about earlier. We just talked about common problems of programming streams in general. Other problems are things that come deliberately and explicitly because of the fact that parallel streams have to worry about stuff like race conditions and so on. So one of the things that the parallel streams framework assumes is that the behaviors that you're passing in to run in parallel will not incur race conditions. And we've talked about race conditions a whole bunch of times, but again, just to reiterate quickly, a race condition is something that can arise when an app depends on the sequence or timing of threads for it to operate properly. And invariably, race conditions occur when you least expect it, and they almost always occur when you have mutable shared state that's being read and written to from multiple threads of control. And if you don't use stateful operations, then you don't have these problems. If you do use stateful operations, you have to be careful. So therefore, you should try to avoid behaviors with side effects. In other words, things that have state. You can read about this at this link here about side effects that can occur with parallel streams, and I'm going to talk through some examples of things that can go wrong. So one classic example is to have stateful Lambda expressions where the results depend on the shared mutable state, which of course is the root of all evil in programs. And this is just a quick recap of something we've now seen a couple of times before, but it'll probably make a bit more sense now that we've been introduced to the streams framework a bit more in general and specifically parallel streams. So here's an example, the Buggy Factorial example, which is in my EX16 folder, so feel free to try it out if you need additional refresher beyond what we talk about here. But basically, you can see that we've got state that can change during the parallel execution of the pipeline in a parallel stream. So here's the factorial method. We make a new single instance of a class called total. You can see total has a field called mtotal, and that mtotal is updated here in the mult method. And because there's no synchronization here, there's no synchronized statement, for example. It's not a synchronized method. We don't use rantrant lock or anything else we might want to do to update this. We don't use an atomic operation, for example. This code, when run in parallel in the different threads of control, will end up trying to simultaneously read and write to mtotal from multiple threads at the same time. And that will cause chaos and insanity. And so you'll end up with race conditions, which I like to symbolize here by cars crashing. That's a good example of two things trying to share the same state at the same time, the same space. And obviously it doesn't work very well. So these are examples of very subtle problems that arise when you have shared mutable state that you shouldn't have. You do not want shared mutable state. You want to be able to use something else like reduce, for example, which will avoid the whole problem of shared mutable state. Another problem you can run into is interference with the data source, which can occur when a source of the stream source is modified within the pipeline. So you can see here we're going to have an example where we have a list of integers. We make that list by going from 0 to 10, non-inclusive, so it's 0 through 9. We box those up into integers. These are ints, now they're integers. We collect them into an array list using toCollection. We could also have just said toList. For kicks, did it this way. So we have a list of integers. So far, so good. Nothing wrong with this. And then we go ahead and we say, make that list a parallel stream, or convert the list into a parallel stream. And then we're going to use the peek operation. The peek operation is intended for debugging purposes or logging purposes. It just looks at each element that comes through the stream for the purpose of logging or debugging or something. But in this particular case, we're evil, and we pass in an operation, which is the remove operation, which will have a side effect, which will remove the item from the list. Bad idea, bad news. And so what'll happen here, if we end up running this in parallel, then the results will be chaos and insanity. And I don't show the results, but if you run the program, you'll see the results. It is chaos and insanity, so it makes you scream. This will also fail with a sequential stream as well, but not quite as grotesquely and probably not quite as quickly. So bad things will happen if you do this because you're modifying the underlying collection. So therefore, the best thing to do is just have Lambda expressions or method references that have no side effects at all, and therefore there's no need for any synchronization. By partitioning the data up into little chunks, then the streams framework guarantees that all the processing is done in such a way where there's no conflicts, there's no race conditions, there's no atomicity problems. And when you join stuff back together again, the stream framework ensures that memory caches are properly flushed in order to make sure the results you end up with at the end are properly converged and harmonized and synchronized and are visible. Here's a simple example. This is an example that we'll talk about. This is the example from the search stream gang program where we're going to create a search results object. And if you look carefully here, you'll see that there's no side effects. Everything that's done in here is a 100% pure function. And all that means is that it has no side effects. It doesn't rely on anything external to it. Everything is self-contained within the context of that particular function. That's the search for phrase function. Down here we can see the isEmpty function or method, and that just checks to see if the size is 0. Once again, completely self-contained, no side effects whatsoever. If you do need to have side effects, then there's various ways you can make that work while still fulfilling the overall goals of trying to use parallel streams efficiently and effectively. So a simple example would be for the program that you're writing, that you're doing for the class, where you're implementing this kind of image crawler. There are parts of that program that have a shared cache. You don't really see it because it's kind of hidden from you, but there's a shared cache that's working, that's using some kind of shared file system or concurrent hashmap and so on. And that image cache is implemented in such a way where you only synchronize exactly where you need to and nowhere else. So it's kind of like the Liberty Mutual commercial of only pay for what you need. And the way this works for our particular example is it uses a concurrent hashmap. And concurrent hashmap is this super cool collection that has special little synchronizers for each of the different bucket chains that come off of the hash table. And when you have things hash, as long as the items that are being hashed hash to different elements in the hash table, then everything can run in parallel as long as you don't hash to the same location, because there's a special synchronizer that uses an atomic compare and swap operation for each different element in the hash table. So if something hashes to location 0 versus location 2, those things can run in parallel without having to worry about conflicting or synchronizing or preventing each other from making forward progress. There's even cool things that are built in so that when you do concurrent reads, there's really no overhead. There's no locking overhead or very little locking overhead. It's only when you do a write and you end up hashing to the same location that there's a short amount of space that has to be locked, but it's also done very efficiently. So the concurrent hash map is a good example of a data structure that's highly optimized for concurrent and parallel processing in multi-core processing environments, and you don't have to worry too much about it making your program run a whole lot slower. It's about as fast as you can get while still sharing stuff. So that's the end of a quick summary of how to avoid some common programming hazards with Java parallel streams. The easiest thing to remember is simply don't share stuff, don't share mutable state, and most of your problems will disappear in terms of synchronization and atomicity and visibility and ordering problems.